Hello, and welcome to this presentation, Understanding Signal Generators. In this presentation, we'll provide you with a general introduction to both analog and vector RF signal generators, including their most important features and applications. Signal generators can be divided into two major categories: analog signal generators and vector signal generators. Analog signal generators are primarily used to generate so-called CW or continuous wave signals, in other words, unmodulated carriers. Analog signal generators can also be used to generate signals with analog modulation, such as amplitude modulated, frequency modulated, or phase modulated signals. In addition, many analog signal generators can also create basic unmodulated RF pulses. And there are also a few special types of purely analog modulation, such as the various avionics standards, that can be created using an analog signal generator. A vector signal generator, on the other hand, can create any arbitrary type of digital or analog signal. For example, a vector signal generator can produce different types of digital modulation, such as the different flavors of Wi-Fi, cellular standards like LTE and 5GNR, GPS and other global navigation systems, etc. They can also produce special non-digital waveforms like multi-carrier CW, where a large number of individual tones are produced. Vector signal generators can also play out so-called arbitrary waveform or ARB files. And unlike analog signal generators, many vector signal generators can introduce various signal impairments, like noise and interferes, as well as fade the generated signals to model real-world propagation effects. Given all the flexibility of vector signal generators, why would anyone ever use an analog signal generator? There are actually many applications whose requirements can, or should, be met using analog signal generators. Analog siggens are used whenever high-quality signals are needed, for example, as a local oscillator substitute. They can be used when measuring basic but essential RF parameters like gain, linearity, bandwidth, etc., and therefore are often a good choice for component tests, such as the development of analog-to-digital converters. In many cases, like receiver testing, we need only basic signals to verify functionality. EMC, or electromagnetic compatibility testing, uses analog signal generators almost exclusively. And for certain applications, like avionics and some military or radar applications, analog signal generators are a good, if not the best, solution. Analog signal generators have two main advantages over vector siggens. They usually cost less, but more importantly, they provide very high-quality signals. Let's talk about this second point in a bit more detail. If there's one thing that analog signal generators excel at, it's creating high-quality RF signals. Signal quality can be divided into three performance areas. The first has to do with frequency, and includes things like accuracy and drift. The next area is level performance. Linearity and repeatability are important concerns here. And last, but certainly not least, we have spectral purity. Both phase and wideband noise, as well as the suppression of harmonics and spurious signals, are key components in spectral purity. It bears repeating that if we want high-quality RF signals, analog signal generators are often the best choice. The most fundamental signals produced by a signal generator are simple unmodulated signals, which have only two configurable parameters, frequency and level. Remember that high-quality spectrally pure CW signals are a very important part of many applications and test scenarios, such as local oscillator substitution, or the testing of analog-to-digital converters. And for those cases where we want to change the frequency and/or level of the CW signals, list and sweep modes can be used to change or switch between user-defined limits, states, or values. In addition to CW signals, an analog signal generator can also generate signals with analog modulation. As we've already mentioned, the three basic types of analog modulation are amplitude modulation, frequency modulation, and phase modulation. Despite the tremendous growth in digitally modulated signals, analog modulation is still very important for many applications, and is still used in a wide variety of design, test, and debug scenarios. A special type of analog signal modulation is pulse signal generation. Most analog signal generators can also create basic unmodulated pulses. The unmodulated RF carrier is essentially switched on and off to create the pulses. Unmodulated means that the RF carrier doesn't change in frequency, amplitude, or phase during the pulse. Pulses can be sent at fixed intervals, but in some cases, analog signal generators can vary the pulse width and pulse spacing by means of a user-defined list. If we want more complex or modulated pulses, such as a chirped or a polyphase pulse, then we usually need to use a vector signal generator. In addition to generic AM, FM, PM, and pulse modulation, there are some other applications for analog signal generators. For example, analog signal generators can be used to create many of the signals in avionics, that is, signals used by aircraft for navigation and landing. These include things like VHF omnidirectional range, or VOR, both localizer and glide slope signals in ILS, or the Instrument Landing System, as well as signals from marker and non-directional beacons. Since the main strength of analog signal generators is their ability to deliver high-quality signals, the primary criteria when selecting analog signal generators are largely related to signal purity. Phase noise, or the short-term stability of the frequency of the signal, is extremely important in many applications, since the effects of excessive phase noise can create many kinds of problems. Similarly, the level of harmonics or other spurious products should be as low as possible. Another important criterion is output power, or more specifically, support for higher output powers. Having a higher max output power helps to preserve spectral purity by avoiding the need for additional external amplification. Secondary criteria include things like switching speed, or how quickly the generator can change the current value of frequency and amplitude, as well as amplitude accuracy in the generated signal. Finally, support for purely analog modulation types, such as the avionics standards we just mentioned, can also be important when choosing an analog signal generator. Now that we've covered analog signal generators, it's time to move on to vector signal generators. But before we get started, we need to first explain the difference between analog and vector signals. An analog signal is defined by a magnitude alone. In other words, it's a scalar value. A vector signal is defined in terms of both a magnitude and a phase. Vector signals are the method of choice for sending digital information, or bits. Let's look at how this might work. For example, we could define 4 different symbols, or states, each with the same magnitude, but with different phases. Each of these symbols, or distinct magnitude-phase pairs, would then correspond to a unique 2-bit pattern. We indicate which pair of bits we're sending by choosing which of these 4 combinations of magnitude and phase we transmit. This type of vector modulation is used in almost all digital modulation schemes. This includes things like LTE, 5GNR, Wi-Fi, Bluetooth, etc., etc. In most cases, however, a much greater number of possible states is used to send more bits for each symbol. But how do we tell a vector signal generator which amplitude and phase values to use when generating RF signals? Instead of representing the vector as a magnitude and a phase, we can use basic trigonometry to represent this vector as 2 magnitudes, a real or in-phase value, and an imaginary or quadrature value. Quadrature just means offset by 90 degrees. In the RF world, vector signals are usually represented as so-called IQ values, consisting of a real and an imaginary value. Using IQ values greatly simplifies vector signal generation and analysis. A vector signal generator, therefore, produces modulated signals using these IQ values, which contain both a magnitude and phase. These IQ values can be provided to the generator in a number of different ways. In most cases, the source of the IQ values is internal to the signal generator. One way of generating IQ values is producing them in real time within the generator itself. Examples of this would be some type of custom digital modulation that uses a repeating or pseudo-random bit sequence as its source, or a simulation of GPS or other global navigation systems. For most types of digital modulation, such as LTE, Wi-Fi, etc., the IQ values are pre-generated internally for some defined period of time, usually in units of frames or subframes. Another common way of generating vector signals is to load a pre-generated file containing IQ values. These arbitrary waveform or ARB files are usually created using either a special software application or MATLAB. Alternatively, IQ can be provided by an external analog or digital source. Note that in both cases, an arbitrary waveform file or external IQ, there is no industry-wide standard for IQ data format, although tools usually exist for converting between different formats. One last important note, you'll often hear the term baseband used to refer to IQ signals before they're converted to RF. So what are the most common applications for vector signal generators? Clearly, vector signal generators are needed whenever we're generating vector signals, such as those found in wireless communications, digital broadcast, GPS, and other global navigation systems. Vector signal generators can also be used to generate multiple signals to simulate multi-antenna systems, such as those used in MIMO or multiple in, multiple out, and in beamforming applications. And as we'll discuss later in this presentation, one of the advantages of vector signal generators is their ability to simulate signal impairments, such as noise, interferers, fading, etc. This is particularly important when testing receivers under real-world conditions. It might be helpful to walk through a block diagram of a basic vector signal generator. As we just discussed, the baseband is where the IQ data is loaded or generated and filtered if necessary. The IQ modulator is used to upconvert these baseband signals to RF. The RF block is where we set things such as frequency, level, etc. Note that in most cases we can also use our vector signal generator as an analog signal generator by configuring analog modulation, such as AM or FM, in the RF block. We'll look at each one of these blocks in more detail in just a moment. But before we talk about the sources of baseband or IQ data, we need to spend a moment discussing something called the bandwidth of a generator. Simply put, the bandwidth of a vector signal generator represents the widest signal that can be faithfully created, and the amount of available bandwidth is a function of the generator design. For example, if we wanted to generate a 10 MHz wide LTE signal, we would need a generator with a bandwidth of at least 10 MHz. Traditionally, most vector signal generators had bandwidths in the low tens or low hundreds of megahertz, but many modern communications technologies, such as 5GNR or some of the newer versions of Wi-Fi, require bandwidths in the high hundreds of megahertz or even the low gigahertz. One of the more important considerations when choosing a vector signal generator is to be sure that it has sufficient bandwidth for the intended application and for future applications as well. A special challenge when using wider bandwidths in vector signal generators is the need to preserve spectral flatness across these very wide ranges or when changing frequency. As signals get wider, the flatness of the signal becomes more and more important. We want to ensure that our generator isn't introducing amplitude errors at any point over a very wide frequency range. For example, making sure that our amplitude error is less than 1 dB over a bandwidth of 2 GHz. This might seem like a somewhat demanding requirement, but remember that many modern modulation schemes require good RF performance over very wide bandwidths. One way of achieving flatness is to run some type of external calibration routine, but this is extremely time-consuming and would have to be repeated every time the signal frequency changes. The more modern approach is to integrate an internal level sensor and adjustment routine into the generator itself. This is significantly faster and has the advantage of preserving flatness even when the generator frequency is being changed. The next question is, how are baseband signals created? Recall that we use the term baseband to describe IQ data before it's converted to RF using the IQ modulator. We can obtain this baseband data in real time from an external source in either analog or digital format, although some conversion or conditioning may be required. We can also create an arbitrary waveform or ARB file externally and then load it into the vector signal generator's ARB memory, usually either via a LAN connection or USB. ARB files can also be created within the generator itself, using a graphical user interface to specify the modulation parameters. And in some cases, IQ data signals can be created internally using a real-time generator, which can produce IQ values for any given duration of time. Note that a single baseband can only process one source of IQ data at a time. That said, many vector signal generators support multiple basebands, whose signals can be created either independently or combined. Let's look at each of these baseband sources a bit more closely. Internal or external generation of ARB files is by far the most common way that vector signal generators are used, but IQ data can also be provided to the vector signal generator over external analog and/or digital IQ inputs. This internal input is used, for example, when the signal is created in an external baseband arbitrary waveform generator. Another common example of where external IQ input is used is where RF signals have been captured or stored as IQ data, and these values are then streamed to the vector signal generator in order to recreate or play back the captured signal. Most often, BNC connectors are used for analog IQ data, and proprietary connectors are used for digital IQ data. And although most vector signal generators are intended to produce RF signals, many can also output their basebands as IQ data over these same connectors as well. The other way of using IQ data created external to the vector signal generator is in the form of an arbitrary waveform or ARB file. Here, the waveform is pre-calculated. The IQ values are not generated in real time. These pre-calculated values are stored in a file containing pairs of IQ values. Arbitrary waveform files can be created in two main ways. The first is using tools such as MATLAB to generate the IQ values. This is usually a very time and labor-intensive, non-trivial task, and requires expert knowledge of things such as signal processing theory and the specific modulation type. A more common method for creating ARB files externally is special software applications, often provided by the instrument manufacturer, with a GUI-based interface for specifying the parameters of a given modulation type. As the name implies, an ARB file provides complete flexibility in the characteristics of the signal. Any arbitrary signal can, theoretically, be created by generating the appropriate IQ values. The main limitation when using arbitrary waveform files is size. The length of the waveform is limited by the maximum number of samples that can be stored in the vector signal generator's memory. Arbitrary waveform files can also be internally generated, that is, without using any external software or computer. In this case, a graphical user interface is also used to specify the desired modulation type and configure the modulation parameters. The created arbitrary waveform can be stored in the generator's internal memory and/or saved as a file. This method is significantly easier than generating an ARB file externally. Let's look at how this is done on a typical vector signal generator. For our example, let's say that we wanted to create an LTE downlink signal. On our generator, we would simply select LTE from the list of available baseband modulation types, and then use a simple graphical user interface to specify the general parameters: uplink or downlink, FDD or TDD, etc. Additional dialogues allow us to configure the characteristics of our signal, as well as to define the contents of our transmitted frame and subframes in whatever level of detail is desired. Being able to perform this kind of signal configuration directly on the generator, as opposed to using external tools, greatly increases the ease and efficiency of defining vector modulated signals. The end result of this process is an arbitrary waveform that can be immediately generated by our instrument and/or saved for later use. As we've just seen, we can create arbitrary waveform files either externally or internally. But the question now is, how do we play out these files? It's important to remember when we create waveforms for most modulated signal types, we usually do this on a frame or a subframe basis. For example, communication standards like LTE, 5GNR, the different varieties of 802.11, etc., all have a frame structure, and when waveforms are created for these standards, the minimum unit is one of these frames. Note, however, there are some types of signals that may not have this defined structure. We can have our vector signal generator play out waveforms in different ways. For example, our generator might produce the waveform only a single time. It might repeat the waveform over and over, or play out the waveform when some type of external trigger signal is received by the generator. We just saw how an incoming external trigger can be used to tell the vector signal generator to play out a waveform. On the other hand, some test scenarios require synchronization with the generated waveform, that is, knowledge of when a waveform or part of a waveform is being transmitted. This is done by means of markers. Markers are a kind of outgoing trigger signal that indicate when a waveform, or a certain part of a waveform, is being generated. For example, we could use a marker to indicate the start of each transmitted frame. The use of markers requires some type of secondary connection, usually a BNC cable, between the generator and the receiver. Predefined arbitrary waveform files can be used to generate very complex modulation schemes and standards, but they have fixed values and relatively short durations. Vector signal generators can also generate signals in real time based on various user-configured parameters. In this case, we start by defining the modulation type, such as FSK, PSK, QAM, etc. Next, the various modulation parameters, such as symbol rate and filter, must be defined. And finally, we define the data to be transmitted. This can be in the form of a file, a repeating pattern, such as alternating ones and zeros, or a so-called pseudo-random bit sequence, or PRBS. PRBS data looks random, but is actually a known repeating pattern. Since the generator is creating these symbols in real time based on the defined parameters, very long sequences can be generated. There's no length limitation, such as there is with static predefined ARB files. And likewise, the generator memory requirements are also quite low, since we're not pre-generating and storing pairs of IQ values. One example of where real-time signal generation is helpful is bit error rate testing, where we want to send a known pattern of bits and determine which percentage of these bits are correctly or incorrectly decoded by the receiver. Another example of real-time signal generation involves simulating GNSS, or Global Navigation Satellite Systems. The best-known examples of GNSS are the American GPS or Russian GLONASS systems, which provide location and timing information worldwide. In order to test the GNSS receiver, a vector signal generator must simulate the signals from multiple satellites over a longer period of time. GNSS receivers require time, often on the order of minutes, to lock onto the signal, and receiver testing may require that the receiver track satellites for very long periods of time, up to hours or days. Furthermore, the GNSS satellites are not fixed in the sky, but rise and set, so the signals from each satellite will be changing dynamically. It should be clear that a static ARB file with the duration of only a few seconds can't be used to test the GNSS receiver beyond basic RF parameters such as receiver sensitivity. A vector signal generator can, however, generate realistic signals and simulate a GNSS constellation over long periods of time by using user-supplied data regarding the satellite constellation, current time and date, receiver location, etc. Now that we've discussed the different ways that IQ values can be generated, let's take a moment to discuss how these values are converted into RF. Vector signal generators convert IQ values into RF by using something called an IQ modulator. When using IQ values for modulation, these are split into two paths, one for I and one for Q. These signals are mixed with an oscillator, and in the Q path, the oscillator signal is shifted 90 degrees. This shift ensures that the I and Q signals do not interfere with each other when they're combined and transmitted. Although it's helpful to understand the basic principles of an IQ modulator, in normal operation, the user of a vector signal generator doesn't need to adjust the IQ modulator or its settings. The last block in our basic vector signal generator is the RF block. This is where we specify the characteristics of the generated RF signal, such as frequency and level. We can also use this block to apply various types of analog modulation, such as AM, FM, phase modulation, pulse modulation, etc. Remember that a vector signal generator is also capable of generating signals with purely analog modulation. Finally, this block also allows us to step or sweep through user-defined values of frequency and/or level, which is very important for some types of testing. The three building blocks of our vector signal generator were the baseband, the IQ modulator, and RF. However, many vector signal generators also allow the addition of signal impairments in the forms of fading, different types of noise and interferes, and IQ impairments. These different types of impairments emulate the kinds of real-world effects seen in RF systems and applications, and therefore the ability to add definable and controllable impairments is important in the design, test, and debug of radio frequency devices. We'll start by looking at noise and interferers. There are four main types of baseband impairments that can be created by vector signal generators. These include noise, or more precisely, additive white Gaussian noise, or AWGN, CW, or continuous wave interferers, impulse noise, and phase noise. Let's start by discussing noise, or AWGN. AWGN stands for additive white Gaussian noise. Additive means that the noise is combined with useful signal, as shown here. White refers to the power of the noise as a function of frequency. White noise has, ideally, the same power at every frequency. And Gaussian describes how this noise changes over time. It increases and decreases over time with a Gaussian or bell curve shaped distribution. Being able to add AWGN to our signal is extremely useful because this allows testing under real-world conditions where noise is a fact of life. By using a vector signal generator to generate this noise, we can create a signal with a definable, controllable signal-to-noise ratio, or SNR. As mentioned a moment ago, this is advantageous when testing things like receiver sensitivity, and when performing bit or block error rate testing. Although this block in our vector signal generator is labeled AWGN for additive white Gaussian noise, it's also possible to generate a noise-only signal with a definable width and power. Being able to generate a pure noise signal is useful in some types of testing, even when no modulated signal is present. Another common type of interferer that can be created by vector signal generators are so-called CW, or continuous wave interferers. These are essentially unmodulated carriers with a very narrow spectral width. CW interferers are commonly used in receiver blocking tests, which test the ability of the receiver to correctly detect and demodulate a signal in the presence of a second interfering signal. A vector signal generator can place a CW interferer near the useful signal, or even within the signal itself. In addition, the power level of the interferer can be adjusted relative to the level of the useful signal. Although it's not difficult to use a second signal source to create a CW interferer and then mix the two signals together, doing this as a baseband impairment provides much more control over the signal position and power, and, more importantly, it eliminates the need for an external second RF generator or second RF path. Although the level of AWGN, or additive white Gaussian noise, does vary over time as per a normal or Gaussian distribution, these changes are relatively small and the noise never goes to zero. Impulse noise, on the other hand, has an on-off or bursty pattern. There are actually many real-world sources of impulse or bursty noise. Some of these are unintentional sources of RF. The typical automobile is full of such sources, such as the sparking of spark plugs, the motors used to power windshield wipers and windows, etc. But there are also numerous intentional sources of pulsed energy, with radar being the most obvious example, as well as some digital modulation schemes that transmit power in short bursts. Some vector signal generators can create impulse noise and add it to the baseband signal by defining the width of the pulse noise, the number of pulses, and the interval between the pulses. Again, the ability to add these impairments to the baseband signal makes it possible to test under more realistic conditions with a minimum of additional equipment and effort. The next type of impairment we'll discuss is something called phase noise. Phase noise is short-term variations in the frequency of a signal. A signal with a fixed, non-changing frequency looks like a thin line in the frequency domain and a stable sine wave in the time domain. If the frequency of the signal changes, we see a spreading of the signal, or skirts, in the frequency domain, and a jittered signal in the time domain. Some amount of phase noise is unavoidable, but excessive amounts of phase noise can cause many different types of problems. For example, phase noise can cause high levels of error vector magnitude, or EVM, in communication systems. In radar systems, phase noise can lead to errors such as the masking of slow-moving targets. Normally, we want a signal generator with the lowest possible phase noise, but in some cases, it's helpful to be able to add a controllable, user-defined amount of phase noise to a generated signal when testing a device. A vector signal generator adds phase noise to the baseband signal by defining the amount of phase noise at given frequency offsets from the nominal carrier frequency. For example, -70 at 100 Hz, -93 at 10 kHz, etc. Increasing levels of phase noise can be seen, for example, in constellation diagrams, where the signal points rotate, leading to increased bit errors. Adding controllable and definable amounts of phase noise to the generated signal can therefore be used to determine the maximum acceptable level of phase noise in components, systems, etc. Now that we've covered noise and interferers, let's move on to the more complicated case of fading. Fading models the effect of real-world signal propagation. Let's look at a few examples. There may be a direct line of sight between the transmitter and receiver, or the signal may reflect or be diffracted from larger objects. Smaller objects with irregular surfaces can cause scattering of a signal. An intervening object may attenuate or block signals entirely for shorter or longer periods of time. Furthermore, relative movements of the transmitter and receiver will result in Doppler shift, or a change in the frequency in the received signal. As we've just seen, in the real world, multiple copies of a signal can arrive with different delays, different levels, and different frequency or Doppler shifts. We can model echoes with similar delays as so-called taps. Each tap has a defined delay, attenuation, and fading behavior. Fading behavior includes things such as the time-varying pattern of the fade. For example, Riccian fading is generally constant over time, whereas Rayleigh fading occasionally will exhibit deep fades. Once we've provided this information, a vector signal generator can then fade the signal appropriately for each tap. Note that many wireless communication standards, such as LTE, require that devices be tested with standardized fading profiles that simulate a wide variety of real-world environments, such as being in a large city or on a high-speed train. The last type of impairment we'll discuss occurs in the transition between baseband and RF, that is, in the IQ modulator or demodulator. When we represent signals as I and Q values, these signals should be, exactly, 90 degrees apart, and should have identical amplitudes. Any imperfections in the IQ modulator or demodulator can lead to errors in converting the baseband signals to RF or vice versa. Note that these errors are a function of the transmitter or receiver, not a function of propagation. Being able to introduce controllable IQ impairments can be very helpful in receiver testing, and vector signal generators can also introduce various IQ impairments, such as quadrature offset, where the angle between the components is not precisely 90 degrees, or gain offset, where I and Q have unequal amplitudes. It should be clear that a vector signal generator represents a significant step up from analog signal generators in the types of signals it can produce. When selecting a vector signal generator, one of the most important primary criteria is bandwidth, since this defines the widest signal that our generator can produce. Remember that the bandwidth required for modulated signals, such as LTE, 5GNR, the more modern versions of Wi-Fi, etc., can require bandwidths in the hundreds of megahertz, so it's a good idea to select a vector signal generator that can meet requirements both today and in the future. Closely related to bandwidth is spectral flatness. As mentioned earlier, one of the challenges in creating very wide vector signals is ensuring a consistent level control over the entire bandwidth, and this flatness is therefore an important specification for wideband signals. Regardless of bandwidth, though, we want to be sure that our vector signal generator is creating as clean of a signal as possible, which means minimizing the level of phase noise, as well as amplitude and other errors that can lead to high levels of EVM or error vector magnitude. Among the more common secondary criteria are things such as output power. Just as with analog signal generators, we want to avoid situations that might require an additional external amplifier, since external amplifiers can degrade the quality of the generated signal. The maximum ARB memory size is also important, since this defines the maximum signal duration of our arbitrary waveform files. It's safe to say that in this case, more ARB memory is always a good investment. And finally, there are numerous other special features or application-specific options that are available on vector signal generators. In this webinar, we touched on some of these, such as the ability to add various types of baseband impairments, but there are many other special applications that can be addressed using the flexibility provided by a vector signal generator. Let's end with a quick summary of the different types of signal generators. We started by looking at analog signal generators, which, as the name implies, are used for generating purely analog signals. The most common applications of analog signal generators are unmodulated signals, or signals with standard analog modulation, such as AM or FM. In addition, some analog signal generators can also generate other purely analog modulated signals, such as the avionics standards like VOR or ILS. The greatest advantage of analog signal generators is they have very high spectral purity. If you're looking for the cleanest, most precise RF carrier possible, then an analog signal generator is often the best choice. Vector signal generators, on the other hand, are primarily used to create signals where both the amplitude and the phase of the signal are important. Most modern communications and other digital data standards use vector modulation, so a vector signal generator is needed to create these signals. The initial creation of vector signals occurs in something called the baseband, where the signals are represented as complex I and Q values, and these are later converted to RF using a so-called IQ modulator. In addition, vector signal generators support a wide range of additional features, such as the ability to add controllable and definable fading or impairments to the baseband signal before it's converted to RF. This is important in emulating the real-world environment in which most RF communications takes place. And finally, vector signal generators can usually also produce purely analog modulated signals, or combine both vector and analog modulation into a single output signal. This concludes our presentation, Understanding Signal Generators. Thanks for watching.